It is not always the case that your data values lie exactly 1, 2, or 3 standard deviations from the mean. Remember, if it is exactly 1, 2, or 3, we can determine those percentages using that previous rule, the 68, 95, 99.7 rule. But if it's not 1, 2, or 3 standard deviations from the mean, what we need to do is determine a standard score, or sometimes called a z-score. And that z-score or standard score is just how many, represents a number, which tells you how many standard deviations you are from the mean, whether you're below the mean or above the mean. So if you're right at the mean, the standard score for the mean is 0, because you're 0 standard deviations away from the mean. So the standard score for the mean is 0. The standard score for a data value that lies 1.5 standard deviations above the mean is just 1.5. That's how many standard deviations away from the mean it is. That's all a z-score or a standard score is. The standard score or z-score for a data value that lies 2 standard deviations below the mean is given as -2. So in these cases, positive means you're above the mean, a negative standard score means you're below the mean. And it's just a position. The position is how far away from the mean are you? So to calculate these standard scores, just a simple formula. It's the data value you're given minus the mean of that data set divided by the standard deviation. And that'll tell you how far away from the mean you are in terms of standard deviations. Positive values on a z-score means you're above the mean. Negative values means you're below the mean. So here's some data. We've got weights of individual quarters. Let's just go back to that scenario we had earlier with the counterfeit coins. I know that the weight of U.S. quarters are normally distributed with a mean of 5.67 and a standard deviation of 0.07 grams. Let's find and interpret each z-score. So look at the notation. It's a z with a little subscript here, and the subscript represents the data value you're working with. So z of 5.74 is calculated by taking the data value, subtracting the mean, and dividing by the standard deviation. So the data value is 5.74. Data value minus the mean, and the mean is 5.67, and we divide that by the standard deviation of 0.07. That's going to give us a z-score, and this tells me how far away from the mean I am. When I make this calculation, I come up with the number 1. So what that tells me is this: 5.74 is 1 standard deviation above the mean. So calculate the standard scores for the rest of the values given in this list. You should end up with the following values. The z-score for 5.88 is 3. That means 5.88 is 3 standard deviations above the mean. The z-score for 5.67 is 0 because it's the mean, which means you are 0 standard deviations away from the mean. The z-score for a mean is always 0. Z-score for the mean is always 0. Okay, so the z-score for 5.53 results in a -2. That means 5.53 is 2 standard deviations below the mean, and the z-score for 5.51 is -2.29 if I round it up, which means the data value of 5.51 is -2.29 standard deviations, or is, 2.29 standard deviations below the mean. So here's a situation where it's not a perfect value. Like we saw earlier with 1, 2, or 3 standard deviations from the mean. When we come up with z-scores that are not perfect, then we need a table to help us interpret the amount of area under the curve with respect to that z-score. So let's talk about these standard scores, or remember they're also called z-scores. Let's talk about those scores in terms of a percentile. Now remember, we're dealing with a normal distribution, and because it's normally distributed, we can find percentiles. And I'm sure you've heard them or read about percentiles. When you take the SAT, your score is in a percentile. You might have scored in the 80th percentile or the 90th percentile or the 70th percentile. We'll see how those values come about with a normal distribution. First, let's just recall what the nth percentile means. The nth percentile of a data set is the smallest value in the set with the property that n% of the data values are less than or equal to it. If a data value lies between 2 percentiles, it's said to lie in the lower value. We'll see how to handle that. So for example, suppose you scored in the 45th percentile on the SAT. This is how that's interpreted. It's interpreted as 45% of the SAT scores were lower than yours. Or you could say that you scored better than 45% of those taking the SAT test. 45th percentile. You can also say this: 55% of the scores were higher than yours, or 55% of the test takers scored higher than you. So that 45 is a cutoff, 45th percentile. It's interpreted as, again, 45% of the SAT scores were lower than yours, or you can say you scored better than 45% of those taking the SAT test. Now we're going to see a table of standard score or z-scored values that will allow us to get some percentiles from some z-scores. So let's do this example. Let's find a z-score of 1.6 on the table, show you how to find that, and show you what the corresponding percentile is and how we can interpret that. So you've got a table at the end of this note sheet, and I'm looking for 1.6. So here is our z-score table. Notice we have a column of z-scores and right next to it a percentile. So a z-score of 1.6 is found right here, and notice 1.6 corresponds to a percentile of 94.52. Okay, so whoops. What happened here? Here we go. So that's we could say that's the 94th percentile. We usually don't state decimals on our percentiles. Okay, so the percentile value is 94.52. So we could say 94.52% of the data values fall below a z-score of 1.6. We could say that 94.52 of the values have a z-score less than or equal to 1.6. Or we can say a data value with a z-score of 1.6 lies in the 94th percentile. Notice the value was actually 94.52, but we usually don't state the decimal on a percentile. We're just going to use that very first value and say that that's the 94th percentile. And remember, that value was obtained from the table. So let's draw some pictures to help solidify this concept. So suppose I was interested in a z-score of 2. And that's 2 standard deviations above the mean. This value right here would have a z-score of 2. For a z-score of 2, if I went to the table, what I would see is a z-score of a percentile of 97.72. Or actually, that's also percentage of data. So 2 standard deviations, or 2 for a value of the z-score, corresponds to 97.72. This is what that looks like with respect to a picture. Mark a line here at 2 standard deviations, a z-score of 2. The value I find in the table of 97.72 represents all the area that occurs below the z-score of 2 and underneath this normal distribution. 97.72% of the data falls below a z-score of 2. That's how we interpret that value from the table of 97.72. We could also say a z-score of 2 corresponds to the 97th percentile. So if someone's height had a z-score of 2 and they were in the 97th percentile, then pretty much they're taller than 97% of the people in that study. Okay, so let's look up another z-score. Let's run down to the table and let's find a z-score of, how about this one? Negative 1.3 corresponds to a percentile of 9.68. Let's see what that looks like on a graph. Negative 1.3 and 9.68. So on my table, on my diagram, I would have the mean right here in the middle. A z-score of negative 1.3 is to the left of the mean, so I'm just going to draw a line to the left of the mean, and I'm going to say that that's negative 1.3. That's my z-score. The table I get, the value I get from the table is 9.68. That means everything below negative 1.3, all the area below the curve, that total amount of area is 9.68% of the total area of the curve. So the value from the table tells you the amount of area starting from the left, stopping at that z-score. So if there's 9.68% of my data that falls to the left of negative 1.3, could you figure out how much data is to the right of that? Yeah, just subtract it from 100. So this part is 9.68. This part here, this amount of area, would just be 100 minus 9.68. And that would give you the portion that I've shaded in green. So that would be 90.32% of the data. So the percentile or percentage of data that falls below negative 1.3 is 9.68%. That's what we got from the table. Based on that number, I can figure out how much is on the right-hand side by just subtracting it from 100. Okay, let me find another. Let's find one more z-score. Let's take a z-score of, we've done a negative. Let's take a z-score of, I don't know, there we go, 0.40. It corresponds to 65.54. So let's go back, 0.40, 65.54. So this is my z-score, not 4.0, it was 0.40, and it refers to 65.54%. Let's interpret that on a diagram. So where does a z-score of 0.40 lie? We know a z-score of 0 is always in the middle because that's our mean. So 0.40 would be somewhere to the right. You don't have to be exact. I'm just going to put 0.40 there, but I know it's to the right of 0. And I'm going to draw my line right there at what I think is 0.40. The number I get in the table refers to what? Does it refer to the percentage of data that's under the curve to the left, or does it refer to the percentage of data that's under the curve to the right? That's what I have to figure out. That's the first thing I need to understand. Remember, on this chart, it's going to give you the amount of data that goes from the left up into that z-score. So the 6.54% that I get from the table represents all the data that is below that z-score. What percent of data is below that z-score? And so 65.54% of the data is below a z-score of 0.40. Based on that, I know that you could figure out what percentage of data would be above a z-score of 4.0. It doesn't give it to you in the table, but you could very easily subtract 100 minus 65.54, and that would tell you how much data is in this blue shaded region. So that value would be 34.46%. Remember, the total amount of area underneath the curve is 100%. If I know one part of it, then I can surely figure out the other part. In this case, just subtract from 100. All right, so let's check out an example. Where did it go? All right, wait a minute. Where did my examples go? Maybe it's below this. Come on, work with me, computer. Okay, this thing is skipping. Give me a second. Well, I lost this page, but then found it. So here we go. Let's look at an example where we can apply that standard score and the table to find percentages or percentiles. So here's what we know. Cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178. Okay, so I got my mean value. Hooray. Whoops, that was bad. So I've got my mean of 178, and I have a standard deviation of 41. So mean 78, my standard deviation of 41. That's going to allow me to draw a diagram. Question is, what percentile is a 20-year-old man, or is a 20-year-old man in with a cholesterol level of 190? So there's a lot of numbers here, and drawing a diagram is going to help me figure out what they're actually asking for. So I'm going to draw a normal distribution. That was pretty crummy. Let me do that again. Okay, and remember the mean is here at 0. It's the mean, the standard score for the mean is 0. It's right there in the middle. It refers to a data value of 178, and I want to figure out what percentile is a 20-year-old man with a cholesterol level of 190. So if my mean is at 178, 190 is going to be above that, to the right of it. But I don't know how many standard deviations away that is from the mean. I've got to figure that out. I've got to figure out that z-score so I can use the table if it's not a nice perfect value. So first thing is to find a z-score of 190. So it's 190 minus 178 divided by the standard deviation of 41. So let's find that z-score. So we get 0.2926 as our z-score, and let's round that up to, well, let's check our chart out and see how that works out. What do we have there? We have a 0.29 that I could look at. Oh, it's increments of 5, so let's actually round that to 0.3. So we're going to call that z-score 0.3. That means I'm 0.3 standard deviations above the mean. So the z-score for 190 is 0.3. So maybe that should be a little bit closer to my 0 mark. So we're going to say here 0.3 is the standard score that reflects a data value of 190. So I'm going to draw my line at 0.3. I want to know what's the percentile for this person with a cholesterol level of 190. So when I go to my table and I look up 0.3, it has a percentile of, let's take a look, 0.3, 0.3, 0.3, I saw it a second ago. Here we go. So a z-score of 0.3 corresponds to the 61.79 percentile. Oh, this is not scrolling great. Damn, I forgot. Whoops, I forgot what that number was. Let me pause this. Okay, so I look up 0.3 in the table. It gives me a corresponding percentile of 61.79, but since percentiles aren't listed as a decimal, we would interpret this as the percentile for a 20-year-old man with a cholesterol level of 190 would be the 61st percentile. Okay, so we have the 61st percentile. What does that mean with respect to cholesterol levels? Well, remember the mean was 178. His cholesterol was 190. That means his cholesterol level is higher than 61% of the population for the 61st percentile. So the higher the percentile in this case, the worse off you are. You really want to be in a lower percentile to have a lower cholesterol level. Okay, so now for part B, we want to actually find what is that data value. What is that cholesterol level that corresponds to the 90th percentile? And if you're in the 90th percentile, that's when usually you are prescribed some type of treatment. So now I want to know, I kind of actually want to go backwards. I want to go to the chart and find the 90th percentile. So we're looking in that second column and we're looking for 90, or as close as we can get to 90. See, I've got a 90.32. Oh, this is making me crazy. It's not scrolling right. Okay, so we'll say 90.32. That's pretty darn close to 90. So we're going to say that's our 90th percentile. The 90th percentile corresponds to a z-score of 1.3. Now that doesn't tell me what the cholesterol level is, but I can find the cholesterol level if I know that z-score. So let's bring that information back up here. So for part B, I'll just kind of partition this off. Part B, I know a z-score of 1.3 corresponds to that 90th percentile. So let's set up a little equation. Okay, so I can set up this equation. I know that a z-score is found by taking the data value minus the mean and dividing it by the standard deviation. The z-score is a 1.3, so I can put that in my equation. I don't know the data value, that's what I'm trying to find, but I do know the mean, and the mean was 178, and I do know the standard deviation of 41. This gives me a real simple equation. I can solve for the data value. And that data value is going to be the cholesterol level that puts me in the 90th percentile. So solve that equation. So when I solve that equation for the data value, I find out that the cholesterol level that would put me in the 90th percentile would be 231.3. So if my cholesterol is at that level, then treatment may be necessary for high cholesterol. All right, let's quickly go through these multiple choice questions, and this will wrap it up. So first question, the graphs of a normal distribution, do they always look the same? Do they always have the same characteristic bell shape? Or they can have any shape as long as they have a sharp central peak. It's B. They always have that same characteristic bell shape. Number 2, in a normal distribution, the mean is equal to the median. Remember, the mean, median, and mode all have the same value, if there is a mode. Okay, number 3, in a normal distribution, data values farther from the mean are less common than data values closer to the mean. Because it's in that tail, it's farther away, so they're less common. Number 4, consider wages at a fast food restaurant where most of the workers earn the minimum wage. Would you expect the wages of all workers at this restaurant to have a normal distribution? So, yes, because wage distributions are always normal. B, no, because minimum wage is not enough money to, whoops, that got cut off, didn't it? Well, let's just say no, because the minimum wage is not enough money. And part C, no, because the fact that no one earns less than the minimum wage means the distribution cannot be symmetric. Definitely part C for number 4. Number 5, in a normal distribution, about 2/3 of the data values fall within 1, 2, or 3 standard deviations. Well, if you take 2 and divide it by 3, that's about 66.6. And remember, we said that about 68% of the data falls within 1 standard deviation of the mean. That's close to 68, so we would say 1 standard deviation of the mean. All right, let's check out question number 6. Come on, scroll for me. Okay, number 6. Suppose a car driven under different conditions gets a mean gas mileage of 40 miles per gallon with a standard deviation of 3 miles per gallon. If you drive this car many times, your mileage on 99.7% of the trips will be between, well, 99.7 reminds me that that percent of my data falls within 3 standard deviations of the mean. So that means if the mean is 40, I'd have to add 3 standard deviations up and subtract 3 standard deviations below, and the standard deviation is 3 miles per gallon. So it'd be 40 plus 9. 49 would be my upper end. 40 minus 9, 31 would be my lower end. Okay, number 7. Okay, same car described above. On about what percentage of the trips will your gas mileage be above 43 miles per gallon? Okay, so let's wrap it up with question 7, the car described above. What percent of the trips will your gas mileage be above 43 miles per gallon? That answer is 16%. Number 8, consider an exam with a normal distribution of scores that has a mean of 75 and standard deviation of 6. If you get an 84 in this exam, your standard score would be 1.5. Number 9, an acquaintance tells you that his IQ is in the 102nd percentile. Well, you can conclude that he doesn't understand percentiles. And finally, number 10. The height of a particular 7-year-old girl has a standard score of -0.6 among the heights of all 7-year-old girls. from table 6.3, you know that B, she is taller than about 27% of all 7-year-old girls. Basically the 27th percentile. Well, that's it. Go to my math lab and do the work. Let me know if you have any questions.